This is Lab 4, Magnetic Braking with Faraday. Introduction. The purpose of this lab is to be able to use Faraday's law and Lenz's law to describe how magnetic field changes when it induces an electric current in a conductor. These induced currents then oppose motion by creating a magnetic field that causes resistance. Some key terms / concepts. We have Faraday's law of induction, which explains how a magnetic flux is changing through a conductive loop and creates an EMF. We have the magnetic dipole moment, which creates a magnetic field that changes as position changes. And then we also have eddy currents, which are currents that circulate and are induced in the conducting tube, which creates its own magnetic field. A brief overview of results. When the bar magnet is dropped through the metal tube, it falls much slower than its typical free fall. The average amount of time that it took the bar magnet to fall through the metal tube was about 3.312 seconds. The system was the bar magnet, and the surrounding was the metal tubes and everything else. The procedure was to determine the magnet's north pole using the magnetometer app, set up the metal tube vertically, drop the bar magnet through the metal tube, repeat this 5 times, and calculate the average fall time, and then model the falling magnet in glow script. For our results, we got the average time of 3.312, and then some possible room for error include that the bar magnet could have been a little damaged. To show the video of us dropping the magnet through the big old tube, and it took about couple seconds, boom. And then just running through code really quick. Some important things include setting up our geometry of the tube. And then we also have the step 1, which was visualizing the bar magnet. And then we also have the dipole. The step 2, edit the function to calculate the magnetic field of a bar magnet. And then so on and so forth. And then step 7 was to calculate the gravitational force on the magnet. And then once applying all this, we run the program and see that as the magnet's falling, you can see that initial fall, and then eventually it the velocity stays the same, but that is initially due to gravity, and then our induced electric field, and then or induced magnetic field, and then it eventually goes down to 0. And then we have the what if the resistivity of the conductor was reduced as close as possible to 0, how would the dynamics of the falling magnet change? Then the magnet would fall even slower, possibly even to stop in the tube. This is because the induced currents would create a much stronger opposing magnetic field, creating lower resistivity and stronger eddy currents. And then we have what if holes or slots were cut into the tube, how would this affect the ring currents in your model? Then the magnet will fall faster. The closed loops created from the eddy currents and cutting slots would break these loops from making the eddy currents much weaker than before, resulting in a magnet with little to no opposing force. The conclusion in this lab, it was demonstrated that the bar magnet falls slower in the middle tube due to the eddy currents and the opposing magnetic forces, which can be predicted with Faraday's law and Lenz's law. The average fall was about 3.312 seconds. The code was edited to replace the behavior, reaching a small velocity as the opposing force reduced the motion. Overall, both the experiment and the code effectively demonstrate how a change in magnetic flux can change the falling of a magnet.